Now let us talk about an important concept that is called gravitational potential energy. We are more commonly denoting it by capital U. Let us first look at the basics of it, then we will try to understand that this word gravitational potential energy was already used in the chapter of work energy power. There you had written the gravitational potential energy as mgh. Now what is the use of defining it again? And there are some other concepts also involved, say gravitational field, gravitational potential. However, so long as this chapter is concerned, those two terminologies are not of much importance because they are essentially dealt in extensive manner in the chapter of electrostatics in class 12th. So maybe we can just give a reference to that, but this is the concept gravitational potential energy which is of larger use. So let us have a discussion on that. First try to see the basics of it. Is that in case you have 2 point masses, say m1 and m2, separated by distance r, small r, then the expression of gravitational potential energy between them is minus g m1 m2 upon r. This is the expression for gravitational potential energy existing between these two masses. If I quickly recap the definition of gravitational potential energy, it was the work done by external agent in bringing these two masses from infinity to this particular situation. Now, if you, let us suppose, assume that a particular body is kept on the surface of the earth. Say this is the earth, and say we are standing on the surface of the earth. Say there is a mass kept on the surface of the earth, small m, and this is the mass of the earth, and the separation between them has become capital R. Then you see, as per this formula, if you apply this formula on this particular situation, then you can say that the potential energy of this mass is minus g capital M small m by r. We say that the gravitational potential energy of this mass kept on the surface of the earth is minus gmm by r. Now the problem arises that in the chapter of work energy power we had said that you can take gravitational potential energy of the surface earth on the surface of the earth to be 0, and if you are at some particular height h, then the gravitational potential energy is mgh. Then what is the use of this new expression? Why are we defining gravitational potential energy in this particular fashion? Now you see, when we were in the chapter of work energy power, there you were throwing small masses, and that too up to small altitude, say 5 meter, 10 meter. But right now when you have come into this chapter in which the masses can be thrown to a larger altitude, maybe several kilometers, 500,000 kilometers, then you see the problem is that acceleration due to gravity is not constant. As you are going above the surface of the earth, acceleration due to gravity is not constant. In the chapter of work energy power, just to simplify our calculations, we had assumed that for 5 meter, 10 meter, the acceleration due to gravity remains constant, and successfully we use the expression small mgh. But in absolute sense, you should understand that the gravitational potential energy on the surface of the earth is given by this expression, and that mgh was just the special case, just the special case of this particular expression. You understand? How it looked like was this. Assume that this is the earth, and right now you are on the surface of the earth. Say this is the point 1, and you have gone to some small altitude h and you are on point 2. Here this h is very small compared to capital R. You understand? Now our question is, what was that small mgh? You have mass m here. This is the mass of the earth. You will find that potential energy at point 1, potential energy at point 1 is minus g m by capital R. This is the radius of the earth, and potential energy at point 2 at some altitude h is minus g m upon r plus h. Now if you take the difference of these two, u2 minus u1, if you take the difference of these two, u2 minus u1, then you can prove it. This becomes very small mgh for this assumption that h is very small compared to capital R. I am trying to say that this expression is the universal one. Whether your movement is small or large, this expression of potential energy will always be applicable. But in case you are moving to some small altitude, then these expressions result into this expression of mgh. It is simply the potential energy difference. This you can say the potential energy in absolute sense, but this mgh was just the potential energy difference between altitude h and on the surface of the earth. This was the reality, and there we had said that you take the gravitational potential energy of the surface earth to be 0, so that at some altitude h it can be easily calculated mgh. But essentially it was just the potential energy difference between these two. The absolute expressions were there, and the difference results into this expression mgh. You understand? So when you are involved with larger altitudes, say you are throwing a stone at a very large speed, and then we are asking what is the height up to which it will go, then for the sake of potential energy you should take this expression and not mgh. But in case the altitudes are very small, then this small mgh works here. You understand? Now let us take the example of escape speed so that we can summarize what we are trying to say, why we are using this minus gmm by r and so on. Let us have the picture of that. Now let us talk about the concept of escape speed. This is simply denoted by v and subscript small e. Consider that this is our earth, and you have an object kept on the surface of the earth. Say it has a mass small m. The mass of the earth is capital M, as we have been indicating all the time, and the radius is capital R. Now the meaning of escape speed is that if you throw this mass in whatever direction you feel like, what will be that minimum speed? You assume that the atmosphere of the earth is absent, and what is that minimum value of speed with which if you throw this mass at any particular angle, then it never comes back to the earth? That means it has gone beyond the influence of the earth. It has overcome the gravitational pull which is acting on it. You see, if you see the energy of this mass which is right now stationary, let us suppose, then the potential energy is the total energy, and that is negative. And negative energy means it is bonded to the system. But the moment energy becomes 0, then this mass will become free and it will escape the influence of the earth. This is another meaning of saying, this is a general saying that whenever the energy of a particle is 0 or positive, then it is free, it is not bonded to a system. But whenever the total energy is negative, it is bonded to a particular system. So escape speed means the total energy of this mass becomes zero. If you talk about the escape speed, then right now you see it had the potential energy, and with the help of this escape speed you are trying to provide it a kinetic energy. The potential energy, you happen to say that this is negative. Potential energy is what? Potential energy for this mass is minus g mm by capital R. Now if you want to make this energy to be zero, that means some positive energy is to be provided, and that positive energy is being provided essentially by this escape speed. So I am writing the kinetic energy due to this escape speed, that is half mv square, and that makes it equal to 0. This is the minimum value of speed which will make the total energy of this mass to be 0. And if you simplify this, then you will find that the expression of escape speed is under root 2 gm upon capital R. You understand? This is the expression you are obtaining for escape speed. If you look at the value of this escape speed on the surface of the earth, in case you substitute the value of capital G, capital M, capital R, you will find this is approximately 11.2 kilometer per second for the earth. For the surface of the earth, this value is 11.2 kilometer per second. If you have some other planets, then the value will change. For example, on the moon it is said that the value is different, and one possible way that we say that there is no atmosphere on the moon is because the velocity of the molecules there is more than the escape speed present there. That is why they escape the surface of the moon and there is no atmosphere. Here on the surface of the earth as well, you will find that the atmosphere extends only up to some limited height. The reason is that on those places above, say around 20 kilometers, the speed is so high that it is escaping the influence of the earth, because the speed of the molecules there is more than 11.2 kilometers per second. Now let us have a discussion on this particular expression which you have obtained. In case you express this gm as gr square, in case we are looking at this expression, as you know that acceleration due to gravity small g, this is capital Gm by r square. So this capital Gm I have replaced by small g r square upon capital R. Then the value of escape speed becomes under root 2 gr. And this expression will tell you that even on the surface of the earth, the escape speed is not same. If you look at the surface of the earth, you assume that the radius is almost same. Then also you have seen that acceleration due to gravity is maximum on poles and minimum on equator. So if you look at this expression, this is small g, at whatever place the value of a small g is large, the escape speed will be large. What I am trying to tell you is that this expression of escape speed as 11.2 kilometer per second is an average value on the surface of the earth. It is not as such that the value of escape speed is same at each and every point on the surface of the earth. Rather, it is more on poles and less on equator. If you are trying to project an object from the poles so that it escapes, the value will be more. The value of escape speed will be more. But in case you are trying to make it escape from the equator, then you will have to put less effort. The escape speed for that object will be lesser. You understand? In case sometimes this value can become larger than the speed of light, then even the light will not be able to escape. If you keep this expression greater than or equal to speed of light, then you will find that even light will not be able to escape from that planet which you happen to call a black hole. For example, everybody is shrinking, the earth is shrinking, Earth is shrinking, and let us suppose a time comes when the size of the Earth is almost the size of a grape. Then you will find mass is same, radius is almost 1 centimeter. Then this value of escape speed is almost equal to the speed of light, and then you can say the Earth has become a black hole. You understand? These are the concepts which are involved with the terms of escape speed. Now, as I was saying that when larger speeds, larger distances are involved, then you should modify the concept of, you can say, conservation of energy. In case you are throwing a mass and it is going up to some height, then you will find that the total energy here will be the sum of kinetic energy plus gravitational potential energy, and the expression used will be this. So let us have an example of that. Let us take an example. Assume that the surface of the Earth is here, and from where a mass has been projected with a very large speed, and that is equal to under root gr. You see, g is around 10 and r is 6400 kilometer. It's a very large speed with which you have thrown the object. Then you have to find out the maximum height up to which it is going. You have to find out the maximum height up to which this mass goes. This is what you have to find out. Consider that the mass is small m, the radius of the Earth is r, and the entire mass of the Earth is concentrated at its center. What I was trying to tell you is this potential energy as mgh will no more be used here, because that was applicable when the heights involved, the altitude involved, they were small. Right now, say this is point 1 from which you have projected the mass, and this is the point where its velocity will become 0. So I am trying to tell you that the conservation of energy principle here will be total energy at 1 is equal to total energy at 2, and the only thing you have to keep in mind here is that potential energy no more will be taken as mgh, rather it will be taken as minus gmm by r. Why? Because larger heights are involved, and at larger height the acceleration due to gravity will not be remaining constant. So if you look at point 1, try to see what is potential energy at 1, what is kinetic energy at 1, and it should be equated to potential energy at 2 plus kinetic energy at point 2. This should be equated to that. Now the potential energy at 1 will be taken as minus gmm upon r and no more mgh. This is what I was trying to stress, because the value of small g does not remain constant, and kinetic energy will be half mv square. So this is half m, v square means this gr. You understand? This is given to you, and this is equal to potential energy at point 2. Now potential energy at point 2 will be minus gm m upon r plus h max. This is the maximum height up to which it is going, and this is very much obvious that at maximum height the speed of the particle will become 0, so kinetic energy becomes 0. You understand? So this is the modified way in which you will be applying the conservation of energy principle. Earlier for small heights you were applying half mv square plus mgh is equal to constant, but when larger heights are involved, then you have to use this expression of potential energy. This is the only precaution you have to take when you are dealing with larger altitudes. And if case you simplify, then you can get the value of h max as capital R. Frequently you see this capital GM is replaced by small g capital R square, and that can give you the value. In case you will be using that expression of half mv square plus mgh, then you will find that this maximum height is coming out to be only r by 2. So that is wrong, because the acceleration due to gravity is not remaining constant. You cannot apply that equation. That could be applied only when the altitudes involved, they were small. You understand? So this is the way you will be progressing so long as the concept of potential energy is concerned. Now, as I said, there is some low profile concept here which you call gravitational field and gravitational potential, but we will be essentially dealing with these concepts in a better manner when we will be coming in 12th. But right now let us have a quick reference to what is the meaning of gravitational field and gravitational potential. Gravitational field and potential is a kind of concept which you can say is the places where you find the influence of any particular object. Say this is the earth, then in all these surrounding areas where you see the influence of this mass, that is called the field. So formally it has been defined. Let us suppose you are at a position small r, then this gravitational field is defined as force per unit mass. Let us suppose you have kept a mass here, then what is the force per unit mass acting on it? That is defined as gravitational field. This will give you the expression, this is denoted by G, and this is equal to Gm by r square. If you look at in vector terms, you will find that it can be represented this way. This is the gravitational field. Sometimes it is also called gravitational field intensity. We will be dealing with this later on. And gravitational potential this is denoted by capital V. This is a scalar quantity is defined as minus Gm by r. But believe me, we do not have to use such expressions here. There is no discussions which are involved in this particular chapter for this, and this will be dealt in a better manner when you talk about electric field and electric potential. So that is all in our today's lecture. Before we go ahead, let us summarize what we all be discussed today. In today's lecture, first we talked about Newton's law of gravitation. Then we talked about acceleration due to gravity. And its variations. Then we talked about a very important concept, that was gravitational potential energy. Related to that was a concept of, you can say, escape speed. And a very low profile topic, that is gravitational field intensity and gravitational potential. we said that the last topic will be dealt when you enter class 12. So this is all for today's lecture. In the next lecture we will be talking about satellite motion and Kepler's laws of planetary motion. Thank you.